Professor Yang received his Bachelor of Science and Master of Science degree from Southwest Associated University in China during the wartime. And in 1945, he went to United States and got his PhD from University of Chicago in 1948. He spent another year in University of Chicago, then went to Institute for Advanced Study in Princeton and became a full professor in 1955. In 1966, he moved to State University of New York in Stony Brook and became Albert Einstein Professor of Physics and the founding director of the Institute for Theoretic Physics. And after his retirement, the institute was renamed C.N. Yang Institute for Theoretic Physics to honor his contribution to physics. Professor Yang made a great contribution to the advancement of our knowledge in physics and received many awards and honors because of his contribution, including the Nobel Prize in 1958. Among his work, the Yang-Mills gauge theory is the foundation of the Standard Model, and the Yang-Baxter equation opened up a new direction, okay, to the integrable model. And of course, his work with TDD on parity variation, okay, is a groundbreaking work. Okay, so we are really very lucky to have him this afternoon to give us a talk on conceptual origins of Maxwell equation and of gauge theory of interaction. So without further ado, let's welcome Professor Yang.
20 years ago, one day, Professor Chen Shenshen said to me, I now really know I'm very old, because when I go to a conference, I would always be the oldest participant. Not only that, the next oldest participant is always 10 years younger than I. So I think probably the same applies to my feeling this afternoon at Taiwan Daxue. I'm going to report to you this afternoon an article which has already been published in the Physics Today with the title Conceptual Origins of Maxwell Equations and of Gauge Theory of Interactions. It is usually said that Coulomb, Gauss, Ampere, and Faraday discovered 4 laws experimentally, and Maxwell wrote them into equations by adding. That is not entirely wrong, but it obscures the subtle interplay between geometrical and physical intuition that were essential in the creation of field theory. First, 19th century. The first big step in the study of electricity was the invention in 1800 by Volta of the voltaic pile, a simple device of zinc and copper plates dipped in seawater brine. Before that, one cannot make any systematic study of electricity. After that, on a very, very small scale, but planned experiments were carried out. Then in 1820, Ørsted, a Dane, discovered that an electric current would always cause magnetic needles in the neighborhood to move. Ørsted's experiment electrified the whole of Europe, leading to such devices as the solenoid and to the exact mathematical laws of Ampere. Ampere was learned in mathematics. He worked out in 1827 the exact magnetic forces in the neighborhood of a current as action at a distance. Faraday was also greatly excited by Ørsted's discovery, but he lacked Ampere's mathematical training. In a letter Faraday wrote to Ampere, we read the following. I'm of entering any fact reasoning. I'm obliged to feel my way by facts close. To feel his way in understanding his experiments. Compile his of research. It is noteworthy that there was not a single formula in this whole monumental compilation. This is an early edition of the 3 volumes of Faraday's work. By the way, I was impressed when I found that the Tsinghua University Library in Beijing had kept a copy of such a 19th century publication, indicating that the librarian or the curator of the library in Tsinghua in the early days was very knowledgeable. Then in 1831, Faraday discovered electric induction. This is a photograph from Faraday's diary of 1831 in October. It shows a solenoid with a coil attached to a galvanometer. He found that if you move the bar magnet in and out of the solenoid, one would generate electricity in the solenoid. Faraday discovered how to convert kinetic energy to electric energy, thereby how to make electric generators. That, of course, is one of the essential steps that made the 20th century possible. This was, of course, very, very important. But perhaps more important was his vague geometrical conception of what he called the electrotonic state. He did not define what this state was. In various parts of his experimental researches, you read about his names for this electrotonic state. Sometimes it's called a state of tension, or a state of vibration, or perhaps some other state analogous to the electric current to which the magnetic forces are so intimately related. This concept first appeared early in section 60, volume 1 of experimental researches, but without any precise definition. One reads in section 66, all matters take on the peculiar state. In another section, the state appears to be instantly assumed. Another section is called the state of tension. Faraday seemed to be impressed and perplexed by 2 facts. First, that the magnet must be moved
to produce induction. A magnet which stays inside the solenoid without moving does not produce electricity. Second, that induction often produces effects perpendicular to the cause. The motion of the solenoid is horizontal, but the current is in the solenoid is perpendicular to it. Faraday was feeling his way in trying to penetrate electromagnetism. Today, reading his experimental researches, we have to feel our way in trying to penetrate his geometric intuition. And of course, that was also the case with Maxwell. When Maxwell started to study Faraday's works, he had to feel his way. Like today, we have to feel our way to try to understand what this geometric intuition of Faraday was really about. Faraday seemed to have two basic geometrical intuitions. First, magnetic lines of force, and second, the electrotonic state. The first was easily experimentally seen through sprinkling iron filings in the field. It is now called H, the magnetic field. The latter, the electrotonic state, remained Faraday's elusive geometrical intuition when he finally ceased his compilation of experimental researches in 1854. He was 63 years old. That same year, Maxwell graduated from Cambridge University. He was 23 years old. In his own words, he wished to attack electricity. Amazingly, 2 years later, he was able to publish the first of his three great papers which founded the electromagnetic theory as a field theory. Maxwell has learned from reading Thomson's mathematical papers the usefulness of an equation which in today's vector form is written as H equal to curl of A. Of course, in Maxwell's time, there was no vector notation, so he wrote it out as three equations, as Thomson did before him. Studying carefully Faraday's voluminous experimental researches, Maxwell finally realized that the electrotonic intensity of Faraday is equal to the vector potential A, defined by the equation H equal to curl of A. He realized that what Faraday had described in so many words was the equation E equal to minus time derivative of A. If you take this equation and take the curl of both sides, we get curl of E equal to minus H dot. This last equation is Faraday's law in differential form. Faraday himself had stated it in words which translates into this formula which is well known today to all students of electricity and magnetism. So today we write this equation or the equation on the previous slide as Faraday's law. But actually, the one who really was able to write down Faraday's law was Maxwell. Comment. Maxwell used Stokes' theorem in his work extensively, which had not yet appeared in the literature. It had first appeared in the 1854 Smith Prize exam, which Maxwell had taken as a student. To prove Stokes' theorem was question number 8 in that year's Smith Prize examination. Thus, Maxwell knew the theorem, and he used it extensively in his papers. Stokes' theorem, of course, today in its generalized form is one of the cornerstones of modern differential geometry. Maxwell was well aware of the importance of his paper 1, of his identification of the vector potential with the electrotonic state of Faraday. To avoid possible controversy with Thomson about the origin of equation H equal to curve A, Maxwell wrote explicitly in his paper that with respect to the history of the present theory, I may state that the recognition of certain mathematical functions as expressing the electrotonic state of Faraday and the use of them in determining electrodynamic potentials and electromotive forces is, as far as I'm aware, original. That's, of course, a correct statement. But then he added, the distinct conception of the possibility of the mathematical expressions arose in my mind from the perusal of Professor William Thomson's papers. So, in this paragraph, you see very clearly 2 things. First, he was very proud of his discovery. Second, he was aware of the fact that he has extensively used Thomson's idea, and he was afraid that Thomson might take offense. 5 years after paper 1, he started to publish paper 2 in 4 parts, part 1, 2, 3, 4, from the year 1861 to the year 1862. The displacement current first appeared in part 3 of this paper 2. It appears in proposition 14, which reads, to correct equation 9 of part 1 of electric currents to the effect due to the elasticity of the medium. That is to say, he added the displacement current to what had earlier been taken as Ampere's law. Maxwell arrived at this correction, according to his paper, through the study of a network of vortices. There are quite a number of diagrams of vortices in this paper too, of which the most interesting one, I think, is this particular one. You observe that what he was thinking of are a network of complicated vortices. Each of the small circle is a vortex, and then each of the hexagon is a larger vortex. And he had arrows showing the motion of the medium because of the collection of these vortices. By the way, and this has not been commented in the literature before, I noticed that there must be a mistake in this in his diagram, because if you look at the second row from the bottom of the hexagons, if you look at them carefully, you will find that they were not, the arrows were not in the right direction. After examining this carefully, I decided that this must be a typographical mistake of the draftsman of Maxwell. Maxwell took this model seriously and devoted 11 pages to arrive at the correction. I made several attempts to understand these 11 pages, but failed. With the correction, Maxwell happily arrived at the momentous conclusion. We can scarcely avoid the inference that light consists in the transverse undulations of the same media, which is the cause of electric and magnetic phenomena. That is to say, light is equal to electromagnetic waves. This is really a momentous discovery of great importance for mankind. Maxwell was a religious person. I wonder, after this momentous discovery, did he, in his prayers, ask for God's forgiveness for revealing one of his greatest secrets? Because of the importance of this discovery, I made several attempts, as I told you before, of how he arrived at the displacement current, thereby the whole 4 equations for electromagnetism. But as I said, I had failed. There have been books and books written about the discovery of the displacement current. None of them explained the procedure by which Maxwell arrived at displacement current. The word displacement did not appear in paper 2. It did not appear in paper 1. It first appeared in paper 2. And once it appeared in paper 2, it became a central idea. So the discovery of the displacement current evidently is a great turning point. And I think this is one of the great puzzles of science history about how precisely he had arrived at the displacement current. Did he really utilize his network of vortices? Or did he merely extracted some ideas from the network of vortices and using the abstraction to write down the displacement current? I don't know the answer to these questions, but I think it is a first-rate historical question worthy of further study. Paper 3 was published in 1865. It had the title, A Dynamical Theory of the Electromagnetic Field. In it, we find the formula for energy density, which we teach to our students today, 1 over 4 pi times E squared plus H squared. In section 74, we read a very clear exposition of the basic philosophy of field theory. In speaking of the energy of the field, however, I wish to be understood literally. All energy is the same as mechanical energy. Whether it exists in the form of motion or in that of elasticity or in any other form, he was referring to the first law of thermodynamics, which was already established at the time. The energy in electromagnetic phenomena is mechanical energy. The only question is, where does it reside? On the old theories, it resides in the electrified bodies conducting circuits and magnets in the form of an unknown quality called the potential energy, or the power of producing certain effects at a distance. In our theory, it resides in the electromagnetic field. In the space surrounding the electrified and magnetic bodies, as well as in those bodies themselves, and is in two different forms, which may be described without hypothesis as magnetic polarization and electric polarization, or, according to a very probable hypothesis, as the motion and the strain of one and the same medium. That was historically the first clear formulation of the fundamental principle of field theory. But Maxwell still believed there had to be an ethereal medium. Why? Because before Maxwell, waves always produce in some medium. How can there be waves in electromagnetism without any medium? So therefore, it is natural for Maxwell to assume that there is a certain medium which he called ethereal medium. My comment. Throughout his lifetime, Maxwell always wrote the equations with the vector potential A playing a key role. After his death, Heaviside and Hertz gleefully eliminated the vector potential A. But in the 20th century, with quantum mechanics, we now know that A has physical meaning. It cannot be eliminated. For example, in the Aharonov-Bohm experiment. '20th century. Thomson and Maxwell had both discussed what we now call the gauge freedom in the equation H equal to curl of A, because this equation, starting from H, does not define A uniquely. We all know you can add a gradient function to A, and that does not change this equation. It was in the 20th century, with the development of quantum mechanics, that this freedom acquired additional meaning in physics and mathematics, as we shall discuss below. The first important development in the 20th century in physicists' understanding of interactions was Einstein's 1905 special relativity, according to which there is no ethereal medium at all. The electromagnetic field itself is the medium. The next important development was the 1930 to 1932 discovery of the positron, which led to Dirac's sea of negative energy particles, in other words, to QED. QED was very successful already in the 1930s in low-order calculations, but was beset, not the reset, was beset with infinities in higher, not solar, higher order calculations. Then in 1947 to 1950, when I was a graduate student and young postdoc, there was the revolution called renormalization. Renormalization was a recipe, not really a theory, which was extremely successful. The latest theoretical and experimental agreement showed that the extra magnetic moment of the electron, A equal to G minus 2 divided by 2, has been measured experimentally and calculated theoretically by renormalization. and the two agree to one part in Abelian. That is a spectacular success. It is mysterious how such a makeshift program called renormalization could be so very, very accurate. It's a mystery which perhaps in future years will be understood better than we do today. With the success of renormalization, during the 20 years between 1950 and 1970, there were, of course, naturally efforts to extend the field theory. There were also efforts to find alternatives to field theory, because although renormalization was successful, it was recognized that it was not enough to describe the new phenomena, especially the new particles that have been discovered experimentally. Finally, in the 1970s, physicists returned to field theory, to non-Abelian gauge theory. Gauge theory did not originate at that time. It had originated earlier in 1919 from the work of the great mathematician Hermann Weyl, who wrote in 1919, "The fundamental conception on which the development of Riemann's geometry must be based, if it is to be in agreement with nature, is that of the infinitesimal parallel displacement of a vector." If in infinitesimal displacement of a vector, its direction keeps changing, that is what was necessary in Riemannian geometry and in general relativity. Then Weyl asked, "Warum nicht auch seine Länge?" Why not also its length? If its direction can change, why not its length can change? So therefore, he figured out a theory in which the length measurement keeps on changing with the parallel displacement of a vector. Based on this idea, Weyl introduced a Streckenfaktor, or Proportionalitätsfaktor, which is written in this formula, in which gamma is a real number. In other words, he identified the infinitesimal length changing factor with the vector potential at that particular point. Einstein criticized this early idea of Weyl's. Then in 1925 to 1926, Fock and London independently pointed out that in quantum mechanics, P minus EA becomes this expression when you replace P by a differential operator. They compared this formula with Hermann Weyl's proportionality factor, and realized that the Hermann Weyl's gamma should be imaginary in quantum mechanics instead of Weyl's proposal that the gamma been real. In 1929, Weyl bought this idea of Fock and of London and published an important paper accepting that gamma should be imaginary. Once that is accepted, Weyl arrived at two things. A precise definition in quantum mechanics of gauge transformation, both for electromagnetic field and for wave function of the charged particles. It's a coupled transformation. On the one hand, it gives a electromagnetic gauge transformation, and on the other hand, it changes the phase of charged particles in quantum mechanics. Second, Weyer found that Maxwell equations are invariant under this combined gauge transformations. So this is the first clear formulation of what is known as a gauge transformation. Weyer's gauge invariance produced no new experimental result. It was very pretty, but it produced no experimental results. So it was regarded as an elegant formalism, but not essential. I remember when I was a graduate student and later a young postdoc, we all knew about the gauge transformation. And mathematically, it's very elegant, but there was no use. The only practical use I remembered was you wait when a colleague gives a lecture. At the end, you would shoot the following question at him. Is your result gauge invariant? If he had thought about it, he would give you a good answer. If he had not thought about it, it would floor him. After World War II, many new strange particles were found. How do they interact with each other? This was the dominant question when I was a graduate student between 1946 and 1948. This question led to a generalization of Weyer's gauge invariance to a possible new theory of interaction beyond electromagnetism. This was born non-abelian gauge theory. Motivation for this generalization was concisely stated in a 1954 abstract. The electric charge serves as a source of electromagnetic field. An important concept in this case is gauge invariance, which is closely connected with 1, the equation motion of the electromagnetic field, 2, the existence of a current density, and 3, the possible interactions between a charged field and the electromagnetic field. We have tried to generalize this concept of gauge invariance to apply to isotopic spin conservation. Isotopic spin conservation was a concept which originated already in the 1930s from the papers of Heisenberg and especially of Wigner. By the late 1940s, isotopic spin conservation was well established. So there was an additional conservation law in addition to electric charge conservation. If electric charge through gauge invariance can generate an electromagnetic field, wouldn't this isotopic spin, conserved isotopic spin, also generate a field? And that is the motivation for that paper. And the result was what is now called a non-abelian gauge theory. Non-abelian gauge theory was very beautiful, but was not embraced by the physics community for many years because it seemed to require the existence of massless charged particles. In fact, I had published in one of my books a description of what happened in 1954 when I gave a talk at the Institute for Advanced Study about the work that Mills and I were doing on the non-abelian gauge theory. And Pauli was in the audience, and he gave me a very hard time. The reason that he was not believing in the non-abelian gauge theory was because he believed that the theory apparently would lead to massless charged particles, which was, of course, both theoretically nonsensical and experimentally not confirmable. Therefore, non-abelian gauge theory throughout the 50s and 60s was considered another beautiful idea, but had nothing to do with reality. Then, starting in the 1960s, the concept of spontaneous symmetry breaking was introduced, which eventually led to a series of major advances, finally to a U1 cross SU2 cross SU3 gauge theory of electroweak interactions and strong interactions, now called the Standard Model. In the 40-some years since 1970, the international theoretical and experimental physics community working in particles and fields combined their efforts in the development and verification of this model with spectacular success, climaxing in the discovery of the Higgs boson in 2012 by two large experimental groups at CERN, each consisting of several thousand physicists. A comment. Despite its spectacular success, most physicists believe the Standard Model is not the final story. One of its chief ingredients, the symmetry breaking mechanism, is a phenomenological construct which in many respects is similar to the 4-pi interaction in Fermi's beta decay theory of the 1930s. That theory was also very successful for almost 40 years after 1933, but it was finally replaced by the deeper U1 cross SU2 electroweak theory. Entirely independent of developments in physics, there emerged during the first half of the 20th century a mathematical theory called the fiber bundle theory, which had diverse conceptual origins. Differential forms of Élie-Cartan, statistics of Hotelling, topology of Whitney, and so forth, global differential geometry by Chern, connection theory by Erisman, etc., etc. The great diversity of its mathematical conceptual origin indicates that the fiber bundle is a central mathematical construct. It came as a great shock to both physicists and mathematicians when it became clear in the 1970s that the mathematics of gauge theory, both abelian and non-abelian, is exactly the same as that of fiber bundle theory. But it was a welcome shock, as it served to bring back the close relationship between the two disciplines, which had been interrupted through the increasingly abstract nature of mathematics since the middle of the 20th century. Comment. In 1975, after learning the rudiments of fiber bundle theory from my mathematician colleague Jim Simons, I showed him the 1931 paper by Dirac on the magnetic monopole. After he digested Dirac's paper, he exclaimed Dirac had discovered trivial and non-trivial bundles before mathematicians. Ordinary electromagnetism uses mathematics of a trivial bundle. Electromagnetism with magnetic monopoles uses fiber bundle theory, which is non-trivial. That is the end of my talk, but it's not the end of this line of development. It is clear that new fundamental ideas, both mathematical and physical, are required to make further progress, in particular, to eliminate the phenomenological nature of the mechanism for symmetry breaking. Thank you.
So, questions?
Showed us how Maxwell theory plus quantum mechanics leads to this concept of gauge invariance, which is Weyl's work. And then a few decades later, we have your work on non-Abelian gauge theory. And in between these two is Abelian gauge theory. So you have people who say Maxwell theory plus quantum mechanics leads to gauge invariance. But then there is a very important step to say, now let's take the Schrödinger equation plus the concept of local U1 Abelian gauge invariance, and we can get Maxwell equations from the gauge principle in quantum mechanics. Which name would you associate it with that? Or is this conceptual step also, was it first advanced in your work together with Professor Mills?
Hermann Weyl pointed out that Maxwell's theory is invariant under gauge transformations. In fact, when Maxwell wrote down his equations, he already clearly sensed there is a fourfold symmetry, but he did not explicitly formulate it. It was Einstein and Minkowski who discovered the rotational symmetry or the Lorentz symmetry of electromagnetism. The second important invariance of electromagnetism was discovered by Hermann Weyl through the gauge invariance. Today, these two invariances together, in some sense, required the structure of Maxwell equations. You might even say that the Maxwell equation follows directly from both requirements.
Yeah, exactly. That is my question. So you say Weyl also understood that. Weyl understood that you can derive Maxwell theory from the gauge principle.
Weyl understood it.
Oh, great.
But it did not produce new results. So therefore, as I said, it was regarded as elegant but useless.
Mm-hmm.
Then came the new particles. And I, as a graduate student, realized that with all these new particles, if you want to know how they interact, you need some new principle. At that time, many people were working on this. For example, there were many papers published in the 1940s, late 1940s, of vector meson with vector interaction, pseudo-scalar meson with pseudo-vector interaction. Books and books were written about this. So this, one of the symmetries, namely the Lorentz symmetry, to invent the interaction between these new particles. I thought that is not enough. One needs some new principle. And where would one get this new principle? From gauge invariance. So if you generalize gauge invariance to a more general gauge invariance, you can have a new principle. That is what is stated explicitly in that abstract that I just read to you. And that was mathematically very beautiful, but as I said, it immediately was set with the problem of what about the massless charged particles, which was discussed in the last paragraph of the paper that Mills and I published. If you read that the last paragraph, you realize that we stated that this is something that we do not understand. And we have tried to resolve it, but without saying it, the implication was that this requires additional studies. That additional studies turns out to have come some 10 years later in the idea of symmetry breaking, which arose from the minds of several people. And then Higgs materialized that idea into one particular model, and that is the Higgs model. And nobody at that time in the 1960s, when Higgs published his paper, and when other people published similar papers, had the idea that it was the right one, because it was ad hoc. It was only one possibility. And gradually, physicists collectively were amazed that somehow it agrees with the experiment when you adjust the parameters. And that is the status of the present understanding of the standard model.
Okay, thank you very much. If I still may, very brief comment, as long as I have the microphone. In spirit, your lecture reminds me of a wonderful talk I heard at Leiden University by Vladimir Arnold, the Russian mathematician who does geometry of mathematical systems. And that talk was rereading Newton's Principia 200 years later. And he talked about how deep the thinking was in Newton's original writing and how you could find new mathematical theorems there. There is also an essay by Arnold. Are you aware of that work? Because I think it would be very interesting and similar in spirit. Okay, I would have to look it up. I'll see if I can find it. It's wonderful. Thank you very much.
Okay.
Let me add a comment. I had outlined for you through several decades, the mathematicians' realization of the concept of a fiber bundle theory. Fiber bundle became really understood as a fundamental mathematical concept by the mathematicians in the perhaps in the 1950s. If the mathematicians, and that development of the fiber bundle theory was completely independent of physics. If that discovery had been made before 1929, before Weier's 1929 paper, because Weyer was a great mathematician, if he had known about the fiber bundle idea before 1929, with his knowledge and interest in group theory, it would be very natural for him to generalize gauge invariance to non-abelian gauge invariance. It would be the most natural thing because he was hooked on the idea of gauge invariance. He was also one of the greatest experts in Lie groups. So these two of his obsessions, he would have combined them together if he had known that the electromagnetism is a gauge theory, is a fiber bundle theory. But somehow fiber bundle theory was not developed or did not mature yet. So it was only in the 1970s that the mathematics of gauge theory, both Abelian and non-Abelian, became identified with the mathematics of fiber bundle theory. So history is very interesting in the time lag between mathematical concepts and the physics concepts.
In the previous, let me get back to symmetry breaking and the Higgs field. Throughout your talk, it's about infinitesimal vector displacement of vector field. But with the Higgs, we have experimentally, we're seeing a scalar. So, and it brings in at least apparently non-gauge forces. Do you have an opinion on that?
Higgs particle is not intrinsic to gauge theory. It is added to make symmetry breaking possible in gauge theories. And that is, as I said, miraculously in agreement with experiment in so many different and yet it's clearly unsatisfactory. And I think my example was a good one. This is very similar to Fermi's beta decay theory. Fermi's beta decay theory, psi, was a revolutionary development in the 1930s. And for the next 40 years, it was used for physicists to understand the beta decay. And everybody was very, very happy about it. But eventually, we know that it is replaced by a deeper theory, which is the electroweak theory. So this 4 psi Fermi theory is in some sense similar, in my opinion, to the Higgs mechanism.
May I ask, therefore, that you do not believe in fundamental scalar fields? You think it will be replaced?
All I can say is I believe it's not the present understanding of a standard model. It's not the final model. In particular, the symmetry breaking mechanism as phenomenologically proposed by Higgs is not satisfactory.
Okay, thank you.
Now, may I move over to the gravity sector? With the tremendous success of gauge theory applying to the 3 fundamental interactions, as you have beautifully lectured, now the first frontier of physics, gravity, starting from Galileo, is now becoming the last frontier. And do you have any comment about how one can possibly bring the gravity sector under the same umbrella of gauge theory? And in asking you this, I was also having in mind of your 1974 paper on the gauge theory of gravity for the pure space. You have any more comment on it?
It was obvious for many years, since the 1970s, that one needs to understand the relationship between general relativity and gauge theory. And it was addressing such a question that I wrote a paper in 1974. I do not believe that paper is correct. But the problem remains a very important problem. That gauge theory and general relativity are very similar. It's obvious. You look at the equations, they are very similar. And yet, Einstein's philosophy does not follow the gauge principle. So therefore, the true relationship between these two is a fundamental question. And I believe that in fact is related to why we have not succeeded in quantizing gravity. These are different problems, but I believe they are deeply related in a way which requires new brilliant ideas.
I think we all in this lecture hall can be happy and grateful to be around and following and participating in physics in this historic time when the Higgs boson was finally discovered. Do you hold out hopes that we may also, within years, see the discovery of magnetic monopoles, which I understand are a real prediction of non-abelian gauge theory?
I have no idea. The monopole idea was very, very beautiful, was appreciated from the very beginning. With the identification of the mathematics of magnetic monopoles with non-trivial bundles, I think that the elegance of monopole theory is greatly enhanced. So therefore, if you buy Dirac's idea that what is most beautiful must be used by nature, then you would say there has to be magnetic monopoles. But on the other hand, there has been enormous number of searches for magnetic monopoles, all of which failed. So one cannot argue against that fact. So I do not know how to answer your question.
Yeah. Professor Lin.
By the way, let me add a thing, because that perhaps is not generally known. I want to make some propaganda for a paper that I wrote with TTU. I think it was in 1975. After Wu and I established the equivalence of the mathematics of gauge theory with the mathematics of fiber bundles, we applied that new concept to rewrite Dirac's paper of the magnetic monopole. You remember Dirac's paper has a quantization rule, namely Eg over h bar c equal to 1/2 times an integer, where G is the magnetic charge of the magnetic monopole. Now, this quantization condition is clearly a quantum mechanical one, because it has h bar in it. So TTU and I asked the question, how about in classical mechanics, in classical electrodynamics? So let us not quantize it. Let us only start with the classical electromagnetism and try to write down classical electrodynamics of a charged particle E and the magnetic monopole G with the electromagnetic field. So we tried to write down that. And that was successful, and that was published in 1975. The net result of that is the classical theory of E, G, and the electromagnetic field is a very elegant theory. However, you find the action integral of this theory cannot be uniquely defined. Like if you do not have the magnetic monopole, the classical E with the electromagnetism has a well-known Lagrangian formalism, and that yields an action integral which is well-defined. If you now include G in it, then we found that you can still have an action principle, but that action integral can only be defined modulo Eg over C. With that formalism, next you would say, if you apply Feynman's path integral, you remember in Feynman's path integral, you have an exponential of I over h bar times the action. If the action is definable only modulo something, then when that is put on the exponent, you would immediately get Einstein's, you would immediately get the Dirac's quantization rule. In other words, Dirac's quantization rule is a combination of Feynman's path integral formalism of dynamics when you have magnetic monopoles. However, we were very happy about that paper of, I think it was 1975. I think it was published in the Physical Review. The next step for Wu and me for the next couple of years was to quantize that, because that was a classical theory. That quantization led to great difficulties. Eventually, Du Dongshen, T.T. Wu, and I together published a paper, I think it was in 1978, in which we claimed we solved the problem through a Hamiltonian formalism. But that was not an elegant thing. I was never satisfied with it. There's new development in this last year. A young theoretical physicist named Wang Zhong in Tsinghua in Beijing solved this problem. And he has published a paper showing how the result for the classical theory of E, G, and the electromagnetic field can be converted through Lagrangian formalism into a consistent theory which yields the Dirac quantization rule. I recommend that paper to you. I forgot in which journal it's published.
Could you please make a comment on the string theory? Is it a way to the fundamentals of physics?
String theory has two aspects. It's a mathematics aspect. It's a physics aspect. I have never worked string theory, so my opinion is formulated only through conversations with experts. My understanding is that string theory in the last brilliant, unexpected contributions to mathematics. In that, through string theory, mathematical facts were proposed, which were very unsurprising to the mathematicians. Having been told by the string theorists, mathematicians were able to prove that these statements were in fact correct. So therefore, as far as I know, modern mathematicians greatly respect the contribution of string theorists. As far as physics is concerned, string theory is not a theory in the traditional sense in physics. So therefore, it has no impact in physics so far. I have never studied philosophy, so I cannot answer your question. But if you review what I have told you in the last hour and a half, you will find that what I was emphasizing were the very simple conceptual origin, the conceptual motivation of some fundamental developments in the last 150 years. I believe eventually, hopefully, new, simple conceptual origins, which have not been dreamed up yet, will be dreamed up, and that would lead to the next breakthrough.
I have to find out what you think about the acceleration of the universe. What's that impact on the theory of physics?
Modern astrophysics is making enormous progress, in particular through the work of astrophysics in the last 30 or 40 years. We have now greater puzzles. Such things like the dark mass and the dark energy are mysterious. When dark mass was first discussed, I was very skeptical because I thought it was just one type of experiment about the revolutionary period of nebula. But later on, there were many new developments which show that this concept of the dark mass has to be correct because there's so many different manifestations. Therefore, it has to be recalled. One has to accept that there is a great experimental puzzle with many manifestations, which does not square with our fundamental laws of physics as we know it today. Then came dark energy, another mystery. I believe that these are very important questions for the next decades. But how they are going to be resolved poses a question which is of a different nature from what we have been talking about this afternoon. What we have been talking about this afternoon was a satisfactory theory which has some elements which are unsatisfactory from the viewpoint of its elegance and it's too phenomenological, as we said repeatedly. But when you come to dark mass and dark energy, a different thing. You are confronting experiments. Whether the resolution of these two different problems are related to each other, I do not know. It could be.
Okay, last question. What's your advice to the career paths of the physics student, especially those who want to study theoretic, high energy or particle physics?
I have had a long career in physics. So these days when I give lectures to today's, I've always been asked the question, what advice I can give to today's graduate students. I do not know how to answer that question because physics today is enormously different from the physics when I was a graduate student. The main difference is the following. In many senses, physics was much simpler in those days. You get the impression that if you take 3 or 4 or 5 fundamental courses and work hard on them for 6 months for each course, you sort of understand everything about everything fundamental about physics at that time. Today, it's enormously different. Every branch of physics becomes many sub-branches. Such disciplines like material sciences did not exist. Nanosciences did not exist. In other words, today's what is defined as physics today is very different from what is defined as physics in my student days. Does that mean that it's unfair to today's students? Yes, in some sense. It's much more difficult for a student of physics today to get the feeling that I have taken enough courses. I now know what were the fundamental things in physics today. That is an impossible task today. But on the other hand, you can turn this disadvantage into an advantage, because that means that there are enormously number of directions in which you can make fundamental progress. And so therefore, yes, the environment is different. And the graduate student today must realize that there's this difference and try to make the best of the new opportunities that are being offered to him.
Okay, let's thank our speaker again for a very enlightening and very interesting talk. Thank you.